Welcome to AcidBase Reactions. So earlier in the chapter, we discussed the Arrhenius definition of acids and bases. So an Arrhenius acid is a substance that, when dissolved in water, produces hydrogen ions. So we have our acid that I'm symbolizing here as HA. When we place it in water, gives us hydrogen ions and our the anion for our base, the conjugate base of our acid. So an Arrhenius base is a substance that, when dissolved in water, produces hydroxide ions, OH minus ions. So we have our substance here, B. We add water to it, and that gives us this HB plus. This is the conjugate acid of our base, and hydroxide ions. So one drawback to the Arrhenius definition is that we can only investigate the acid-base nature of a chemical when it's dissolved in water. If we dissolve our acid or our base in something else, our chemical in some other solvent than water, we can't say whether it's an acid or a base, or neither. And that's one of the problems with the Arrhenius definition. So another commonly used definition is called the Brønsted-Lowry definition of acids and bases. The Brønsted-Lowry acid, then, is a proton donor. So again, we have the same chemical reaction that we had with the Arrhenius acid, because we have our HA in water gives H plus and A minus, only in this case, this H plus, the hydrogen ion, is now what we're calling a proton. Because of course a hydrogen ion, hydrogen starts out with one proton, one electron. If we ionize the hydrogen to become a hydrogen ion, we've removed that one electron, so now all we have left is a proton. So a Brønsted-Lowry base, on the other hand, is a proton acceptor. So here we have our base, we add the H2O, the water, we end up with Hb plus and OH minus. So again, we still have the same chemical reaction that we had for the Arrhenius definition, only in this case, we're now looking at the base in terms of not producing hydroxide ions, but now we're looking at it, it's accepted this H plus. We've gone from B to Hb plus. Now, B might have a charge, it might have a negative charge, and so if that has a -1 charge, then this would be uncharged, this would be neutral, but that doesn't matter. Whatever the charge is there, the charge will be +1 higher than that Q. So in this way, the base has accepted a proton from the water. So in this case, the water then, because it's donating the proton, the water there is acting like an acid. A Brønsted-Lowry acid, at least. So, let's examine an acid-base reaction between hydrogen chloride and sodium hydroxide. So we have hydrogen chloride plus sodium hydroxide gives us sodium chloride and H2O, water. So note that the hydrogen chloride is acting as the proton donor, and the sodium hydroxide is acting as the proton acceptor. So that means that hydrogen chloride is our acid, and sodium hydroxide is our base. Note that Arrhenius would also give us the same names. We would say that this is an acid, and this is a base, because when we put this into water, the hydrogen chloride will dissociate into hydrogen ions. That makes it an acid. The sodium hydroxide dissociates into sodium ions and hydroxide ions. That will give us hydroxide ions. So we're producing hydroxide ions. That means that sodium hydroxide is a base. But in this case, we no longer have to be doing this in water. With Brønsted-Lowry, we don't have to have an aqueous solution here. We'll still be creating water with our reaction. So there will still be water around, but we could have some other solvent. So we're no longer fixed to looking at water. So hydrochloric acid, sodium hydroxide, and sodium chloride are all strong electrolytes. So they all exist in solution as dissociated ions. So we have H plus Cl minus plus Na plus OH minus yields Na plus Cl minus plus water, H2O. So our net ionic equation then, because our sodium and chloride ions aren't doing anything. We then have H plus OH minus yields water. And so in this equation, the hydrogen ion is the proton donor, it's the proton, and the hydroxide, the OH minus, is the proton acceptor. So, now let's examine an acid-base reaction between acetic acid and sodium hydroxide. So we have the acetic acid plus sodium hydroxide yields sodium acetate and water. So note now that the acetic acid is the proton donor, and thus it's the acid, which is why we call it acetic acid. And the sodium hydroxide is the proton acceptor, and thus the sodium hydroxide is our base again. So acetic acid is a weak electrolyte, so the complete ionic equation looks like this. So in this case, the acetic acid remains, most of it remains undissociated, it remains together in the molecular form. So we have acetic acid plus sodium ions plus hydroxide ions yield sodium ions plus acetate ions plus water. And that means that now our net ionic equation is the acetic acid in molecular form plus hydroxide ions yield the acetate ion plus water. And so again, in this equation, the acetic acid is our proton donor, and now hydroxide is our proton acceptor. So the hydroxide is our proton acceptor, whereas on the last slide, it was the sodium hydroxide. Right? But it's that hydroxide is still coming from the sodium hydroxide, so the sodium hydroxide is still our Brønsted-Lowry base. So acid-base reactions like this are often called neutralization reactions because the acid and base are neutralizing each other in order to produce water and a salt. Not necessarily table salt, sodium chloride, but some salt. In the last case, it was sodium acetate. In the first case, it was, in fact, sodium chloride. So, now let's look at acid-base titrations. So, with volumetric analysis, which is a technique for determining the amount of a certain substance that and we do this using a titration. A titration involves delivery of a measured volume, usually from a burette. So a measured volume of a known concentration of some solution. This is our titrant. Into a solution containing the substance being analyzed. That solution we call the analyte. So we need to know how the titrant will react with the analyte, and we also need to know the reaction must occur quickly. So if the reaction doesn't occur quickly, then we can still do a titration, but it's going to take a really, really long time. Now, a titration already takes a decent length of time for us to perform because we're doing the reaction relatively slowly. We're adding small amounts of one solution, the titrant, to the other solution, the analyte. And so, because we want to know exactly how much of that titrant we need to add in order to react fully with the analyte. So, we need to know what an equivalence point is, which is also sometimes called the stoichiometric point. So this is the point in the titration where the number of moles of titrant that we've added is equal to the number of moles of analyte that were present initially in solution. So we often use an indicator, a pH indicator, an acid-base indicator, to mark the equivalence point for an acid-base titration. The indicator changes color at or near our equivalence point, and the point at which the indicator actually changes color is called the endpoint. Note that the endpoint and the equivalence point are not necessarily the same. In fact, most of the time they're not. The equivalence point is when we have exactly a stoichiometric ratio, a 1-to-1 mole ratio of the titrant and analyte that we had. So we have added exactly the same quantity. So with our acid and base, they are exactly neutralized. But the endpoint isn't necessarily at that same point because the endpoint is where the indicator is changing color. Now, the indicator may change color at the equivalence point, or it may change color slightly before or slightly after. Now, most of the time, we want to be looking at an indicator, we want to be using an indicator that will change color slightly after. Now, by slightly, I mean just very slightly. In most cases, it's 1 to 2 pH units after the equivalence point, but 1 to 2 pH units can occur very, very rapidly in a titration. You may have less than 1 drop change from the equivalence point to the endpoint. So for an acid-base titration, we generally use a strong acid or a strong base as the titrant, and often we use phenolphthalein as the indicator, although it depends on exactly what our analyte is. We generally use phenolphthalein if we are titrating a strong acid as our analyte, and we're using a strong base like sodium hydroxide as our titrant. So we're going to examine acid-base titrations in more detail in Chapter 15. So if you want to look at acid-base titrations in greater depth, look at Chapter 15 or watch one of my videos from Chapter 15. So that was acid-base reactions.